Kachenga. Kachenga, are you there?
Hi, everyone.
Hi, we can hear you.
Yeah, so welcome to our second meeting for the presentation of SIAM. Maybe, I don't know, Brian, should you wait a bit for some people to join? Brian?
I think we can go from there.
I can't hear you. It's like your mic is muted.
I think we can go from there. Others will join us on the way. Kachenga, can you hear me? Okay.
Can you hear me, Brian?
Yes, I can hear you. I was saying I think we can go from there. Others will join us.
I can't hear you. I can't get you. It's like your mic is muted.
Oh, really?
Yeah, I'm muted, Brian. I can hear both of you.
Yeah,
I can hear both of you too.
Yeah.
Okay, then let me share then if Kachenga can't hear me. Okay, welcome all of you to the SIAM Talk series. So we decided to be hosting these talks for the rest of the semester. So today, our speaker is Titus Nyarko Nde, and it's going to take us through dark matter, hollow density calibration, as this will lead to completion of his comprehensive exam, which is about to defend in a couple of weeks from now, I think 2 weeks from now. So Titus, welcome. Thank you very much.
All right, thank you very much, Brian. Thank you for the opportunity. I hope you guys can hear me.
Yes, we
Okay.
can.
Okay, great. Yeah, so today I'll be talking to you about dark matter halo density calibration. And in this talk, I will take you through the following outline. We'll look at some general introduction, and then I also give you a general summary of the seed papers I considered for this, for my comp exam. And then we'll look at some cosmologies and simulations. We'll also have a look at some analytic density profile models that are already existing in the literature. And then I'll also take you through my computing artifact, what I am working on now. Yeah, so when we talk of dark matter, we are talking about this hypothesized region that is like a hypothesized region of gravitationally bound objects. And this region is usually dominated by invisible objects that we have not yet detected yet. So dark matter is actually inferred. So one of the ways we infer dark matter is if we look at the motion of gas and stars in galaxies. So for instance, if you take a spiral galaxy and then the galaxies orbit around the center, the speed at which they are moving so fast that the luminous matter in that galaxy alone could not account for that speed. And if that galaxy is made up of only that luminous matter, then gravity could not hold the stars together. They will just move apart from each other. So in that situation, we are able to infer that there is some kind of extra matter in the galaxy, which is that we have not yet detected. And the current standard model of cosmology actually shows that our universe is made up of about 68% dark energy and then 27% dark matter. And then this dark matter is made up of about 85% of all matter in the universe. So baryonic matter constitutes only 5%. And when we talk of baryonic matter, you can just think of it as everything you know on Earth. Everything that is on our periodic table is baryonic matter, and it's only 5% of our universe. So actually understanding the nature of this dark matter helps us to also understand the dynamics of our universe. Now, this is the big picture of what I am doing. We have theories and simulations that in the past, like we even have analytic models that were developed based on our understanding of the universe. But these days, with advancement in technology, we have like many telescopes are being built day in, day out to collect high quality data. And then we end up finding some kind of discrepancy between our theories and then what observation. So there is the need to reconcile the two. And that is the whole big picture of what I'm doing. So for instance, in this figure, this is a simulated halo. And this yellow spot, this yellow region is the center of the halo, and that is where most of the matter is. So this yellow spot means what? Higher density, and it constitutes somewhere on this portion. And then as you move out of the halo, the density reduces in that order. And then this image we are seeing here is from observation. And this image is actually from the recent James Webb telescope that was launched. And then this is a galaxy cluster we are observing here. And one of the ways to calibrate the density in observation is to use the galaxy number density. And with that, we are also able to get a curve like this for the density profile. But by then, we realize that these halos also have outer regions. So actually, I actually indicated all the 4 papers I'm considering in my synthesis, which part of the density calibration they focus on. So the Hansen et al. Paper focuses on impact of baryons on dark matter density calibration, which is almost like the center of the halo, the inner region. And then we have the Demir and Kraftstoff paper, and then the Demir 22, which also focuses on the outer regions. And then we have this Shin et al. Paper that focuses on calibrating density profiles from observations. Now, so this is the list of the 4 seed papers that I am considering for this present. Sorry, I'm being interrupted. Okay, so these are the 4 papers I'm considering. So the paper 1 is the Demir and Kraftstoff paper that focuses on calibrating density profile of the outer regions. And then the paper 2 by Shin et al. Paper that focuses on, that uses observational data to calibrate density profiles. And then we also have paper 3 by Demir 22. So this paper is also focusing on the outer regions, and then also the region between the inner and the outer region, which we call the splashback region. So, and then the last paper talks about the impact of baryons on density calibrations. Now, so this is a high-level summary of all the 4 papers. So for instance, in paper 1, the main focus is to calibrate density profiles, but their attention is on the outer region. And they use data from a simulation, from M-body simulations. And then their support is that we have NFW and Einasto profiles that precede this paper. And these profiles usually poorly predict density profiles. So in their analysis, they proposed a new fitting equation, like a new analytic function. And then for the first time, they have detected that there is actually a feature that is separating the inner region of the halo from the outer region. We call it the splashback feature, which I will show you in some slides from now. And then they are trying to say that since this feature is being detected in simulation, then it means that we should be able to detect the same feature in observational data as well. And then paper 2 by Shin et al. Also focuses on calibrating density profiles. And then they use observational data from the Atacama Cosmology Telescope, data release 5, and then data from the dark energies of the year 3 results. And then they used this procedure we call the halo occupation distribution, and then also adopted a DK14 profile with some perturbation theory to calibrate their density profile. But so these people too were able to observe the splashback feature for the first time using observational data from, like, we call it the SZ data, the Sunyaev-Zeldovich effect. So though they are using observational data, so just as Demir and Krastov, they've also been able to detect the splashback feature. But the problem is that the splashback feature, the mass distribution in this region is not yet well understood. So it's usually difficult to calibrate the density profile in this region. Then the paper 3 is also focusing more of understanding the mass distribution in this splashback feature. And they also use data from M-body simulations, but they came out with an approach where they have to they present an algorithm that basically separates the particles in the inner region from that of the outer region. So, yeah, and then they also found, they also found out that single scale fitting equations like the previous NFW and Einasto profiles they are not sufficient in calibrating density profiles. And then paper 4, all the 3 papers I've mentioned above assume that they are using dark matter only models. That is to say that they assume a halo is made up of only dark matter. So even though halos are dominated by dark matter, but they are made up of baryons as well. So the last paper is focusing on baryonic effects. What if baryons have significant impact on our density profiles? And that is basically what they did. But they actually found out that baryonic effect on high mass halos is very low. Now, so with all this in mind, we have several experiments that were performed, and then we have pretty much sometimes varying results. And sometimes these results become so different that we can no longer ignore their differences. So for instance, even for the same experiment, I give you the cosmological parameters for their year 1 results and that of year 7 results. And for instance, for the density fluctuation, which we call the sigma 8, we realize that there is significant differences between the 2 results, even for the same experiment. And sometimes we have varying results from different experiments that cosmologists tend to wonder which experiment is giving us the better calibration of our universe. So for instance, this is what we call the sigma 8 tension, which is basically the density fluctuation. So you can just think of it as like the density over a unit area, like in the entire space, So we also notice that this sigma 8 results, same colors means that this sigma 8 was calibrated from the same data set, the same set of data. But even with that, we could see some significant differences between the sigma 8 calibration of results from the same data. So it's kind of trying to get a better picture of what this sigma 8 is actually. And this we are seeing here is the sigma 8 calibration from the standard model of what cosmology that we have. So we tend to have these varying differences that a lot of research is being conducted to really understand this, because getting this parameter correct helps us to understand our universe better. Now we also have these analytic density profiles that are in existence that we use to calibrate density profiles. So this is the NFW profile, and this is the critical density. Yeah, so these 2 parameters combined actually gives us what we call the scale density. And then this is the radius, the distance to the halo center. And then this is a parameter we also call the scaled radius. So the scaled radius is giving us R200 over C. So this C parameter is actually the concentration parameter. And then the R200 is the radius within which the density of the halo is 200 times the mean matter density of the universe. So sometimes you could see C attached to it to tell you the critical density, or M attached to it to tell you that the mean matter density. And then, oh, wow, what is wrong? And then we have the Einasto profile as well, that is also being calibrated. So this alpha parameter actually controls how the density parameter slopes, like the slope of the density profile. Then the DK14 profile, this Dimi and Krastov paper, which is one of the papers I'm considering in this thesis, actually proposed an extension to the Einasto profile, because the Einasto profile only fits the inner region of the halo. So they proposed an extension to it to be able to fit the outer region of the halo. So they actually introduced this term, which is a transition term, and then the outer term, which is being calibrated by a power law and the mean matter density of our universe. So the outer term is actually given by this equation. Now, but the problem is, these equations I've shown you here are actually 3D density profiles, but we actually observe our universe, the entire space, in 2D, not in 3D. So 3D density profiles are only readily available in simulations. Okay, but in observations, we can't really get them directly. So in observations, we have this, we call the sigma. And it is basically, like mathematically, the sigma is just basically taking an integral. It's just basically taking integral of the 3D density profile. Now, but observationally, like, this sigma is actually difficult to calibrate, because we can calibrate this sigma from something we call magnification effect. And by magnification effect, we mean a situation where magnification effect is an effect of galaxy weak lensing, and it makes the galaxy to appear brighter and bigger on the sky than its actual size and brightness. And this magnification effect is usually difficult to calculate, because before you compute it, you will have to know the size of the galaxy before the magnification took place. So what we now tend to be interested in is something we call the delta sigma, okay? And this delta sigma we call the excess surface density. It's just basically the mean surface density within a certain radius minus the actual surface density. So if you think of this statistically, this is more or less like the actual data minus the predicted data, and it's just basically noise. So this delta sigma becomes so noisy to model. However, it is easy to calibrate. We can easily calibrate it from galaxy weak lensing. Okay, so we can easily calibrate it from gravitational lensing using this equation, where this parameter is just basically the tangential shear, and then this is the critical surface density. Okay, so even though this parameter, this delta sigma is difficult, like it's noisy, it is rather the easiest one to measure observationally. So it becomes really difficult to model the delta sigma as well. Now I give you, this is a picture of the analytic models, and then this is an observational data from the Buzzard simulation. So we actually realized that all the analytic models do not actually capture the detailed shape of this density profile. So the main problem is we want to have a calibration technique that will calibrate these density profiles at least better than the existing analytic models. And this is the slope of the 3 models. And as we can see here, this is the splashback feature. Okay, so this is a region that is separating the inner density profile from the outer density profile. And the mass distribution in this splashback feature is still poorly understood, that it becomes difficult to calibrate. But among the 3 models, it's only DK14 that accounts for this kind of feature in our data set. Yeah. So I will take you through the current status of the field. Okay, so for us to observe halo density profiles, like in observations, we can measure them from what? Weak lensing. And by weak lensing, we are just talking about the bending of light due to the presence of what? A massive object. So if you look at a galaxy in the sky, from your line of sight, you might think that galaxy is just like you can draw a straight line from you to that galaxy. But sometimes it is not. It's actually, the light from the galaxy is actually bent by another galaxy that is possibly between you and then that galaxy you are seeing. So we call this effect basically weak lensing. And by weak lensing, we are able to calculate the richness mass relation, and then there's this thing also called the concentration mass relation. So which I will not be going so much in details. And then we can also use the halo occupation distribution, which I mentioned earlier. One of the papers used this, and it's basically the number of galaxies per a halo of a given mass. And we can use this technique to calibrate density profiles as well. We also have the galaxy number density, which is basically calculating the number of galaxies per unit area, or like if you're considering the 3D density, then per unit volume. Yes. Oh. Okay. So, but the problem is in experiments, this kind of data usually come with some kind of systematic effects. And one of the systematic effects is dilution effect. So that by dilution effect, it means that if you look at a galaxy cluster from your line of sight, because of weak lensing, sometimes, so basically we have the observer, then we have a lens galaxy, we have the source galaxy. So if you look at the galaxy through your line of sight, sometimes you mistakenly count galaxies that are not part of the cluster as being part of the cluster, which we call the dilution. So if it happens that way, the galaxies that are in front of the lens galaxy, if you count them as part of the source galaxy, they are going to dilute the weak lensing signal, because they actually don't have any signal, but you are counting them as if they have a signal. So we call it the dilution effect. And then we also have this miscentering effect. One way we calibrate, so from the halo center, if you observe a halo, one of the techniques is to use the brightest halo center as the center of the halo, like the brightest portion of the halo as the center of the halo. But oftentimes this is not the case. Sometimes the brightest portion of the halo is actually not the actual center of the halo. So we end up to have this kind of miscentering effect as well. And one of the ways that we detect miscentering is to use X-ray calibration. X-ray calibrations are perfect, but the problem is that they are limited in their sample sizes. So we have to find a way. So sometimes you find people using a boost factor to correct for some of these systematic effects in the data. Now, with all this is a synthesis matrix. And then this matrix is just basically identifying some of the major themes that cut across all the 4 major papers. And then we try to see what each paper talks about this theme. So for instance, we have the outer density profile. And for paper 1, they realize that the outer density profile actually depends on a parameter we call the peak height, which is a dimensionless parameter, or the mass accretion rate. So the mass accretion rate is the rate at which the galaxy or the cluster accumulates mass over time. Okay, and then paper 2 also says that, okay, the outer density profile is not well calibrated by the HOD and then the perturbation theory technique they considered. Paper 3 says that, yes, the outer density profile depends on mass accretion rates. And then the outer density, like the outer region of the halo, is dominated by something we call infalling matter. And by infalling matter, we mean that particles that are falling into the halo for the first time. So these particles are not in orbit. They are just falling into the halo for the first time. And then these people also detect that as you move out of the halo center, as you approach the outer region of the halo, dark matter dominates. So the halo center is dominated by baryons, but as you move from the halo center, then dark matter begins to dominate everywhere. Now, what about the splashback feature? So the splashback feature, people one says that, okay, the splashback feature exists, but it is much deeper when the mass accretion rate is higher. So it's linearly correlated with mass accretion rate. And then these people also detect the splashback feature, but they also realize that the location of the splashback feature is consistent in their two measurements using weak lensing and then galaxy number density. Paper 3 also identified the splashback feature, but by then they said it is steeper and occurs faster for high mass halos. So that is basically almost saying the same thing as paper 1. Paper 4 didn't consider this. So when it comes to the mass accretion rate and peak height, paper 1 identifies that the density profile highly depends on these two factors. And then the mass accretion rate can also help us to understand halo formation and evolution. And then paper 3 says that density profiles are highly dependent. So they are just, paper 1 and paper 2 basically have so much similarity in their results. Paper 4 did not consider this. Now the problem is, based on the image I showed you previously, another problem is how to calibrate the halo boundary. How do you say that, okay, this is a halo boundary? So just a quick recap. If I should come back to this halo, we have this halo we have here. And then sometimes calibrating the halo boundary is very difficult because we realize that this is another halo. Over all the bright portions you are seeing, these yellow bright portions are actually halos. And these halos are connected by these things we call filaments. Okay, so sometimes calibrating the halo region becomes difficult. So we try to see what are these 4 papers saying. The 4 papers set a boundary which we call the virial radius as a halo boundary. Paper 2 sets the R200C, which is just the radius within which the halo density is 500 times the critical density of our universe. Paper 3 just sets everything, both the inner and outer region, as the halo boundary. Yeah, and then paper 2 also uses the mean like R200M. And then we also realize that Einasto and NFW profiles are not able to capture the outer region and especially the mass, like the density profile within the splashback region. And then these people are also saying that the Einasto and NFW profile do not capture the splashback feature. The same thing as that of paper 3. The splashback feature depends on mass accretion rates. And then, yeah, this is not well understood, so we can capture it better. Paper 4 says that Einasto is better than NFW, but both of them rather underestimate the density profiles. So this is what we are saying. This is the halo inner region. And then we have this region we call the splashback region. So it just basically the region that separates the inner halo density from the outer halo density. But we can see this feature much more clearly when we check the slope of the density profiles. Okay, so this is the region we are talking about, and the mass distribution in this region is very poor, like it's so poorly understood that it becomes difficult to calibrate it. And now this line is the NFW profile. And we realize that for the inner region, NFW is doing pretty much good, but from that point onwards, within the splashback region and in the outer region, NFW just poorly calibrates the density profile. So this is actually a figure from one of the papers. Now, in all this, what can we learn? We know that the analytic density profiles we have in the literature poorly calibrates densities. And another problem is that we are not able to quantify uncertainties on prediction using these analytic density profiles. Now, when we talk about halo evolution, we are not able to like observe the entire lifetime, like we cannot observe the entire evolution of a halo in one's lifetime. The evolution takes millions and billions of years, but we can simulate them. Okay, so the idea is that possibly if we simulate the entire time series of a halo evolution, then maybe this could help us to understand the dynamics of the halo and be able to predict the density profiles much better. And then, of course, I mentioned this earlier, the splashback region, we still don't understand the mass distribution in this region so much. And then solving observations, there is actually no unambiguous way of like handling the observational systematics. So which means that we need like efficient modeling strategies to be able to fill in this gap. And then we also find that low mass halos have a lot of statistical uncertainty. So because of that, a lot of studies actually eliminate low mass halos from their analysis. So they just ignore them totally. So like in our case, we actually think instead of eliminating low mass halos entirely, we could also get information from them. So maybe we can put them into some kind of mass bins and then just randomly sample some halos from every bin so that all the mass bins are equally represented. Okay, so in our situation, we actually use a parameter we call the peak height. And we're using the peak height because the peak height allows us to compare the halo masses across redshifts. Okay, so if I say redshift, I'm basically talking about how far the halo is from us. Okay, so this is my ongoing research, and this is what my computing artifact is based on. So the computing artifact is just basically using machine learning techniques to fill the first two gaps I've listed here. The idea is to get better predictions and then also be able to quantify uncertainties on our prediction. So these are some of the uncertainty quantification techniques in the literature. The first one is the Monte Carlo dropout. We have deep ensembles, we have Bayesian neural networks, we have mask samples, which is a recent algorithm. I think, yeah, the intuition behind this algorithm, I think, is really cool. We have random forest. I think there are several others that we can list. Yeah, but in this artifact, I used just the first two, but at least we should know that there are several others that can do the same thing. So these are some of the uncertainties that could exist in a data. We have the arithmetic uncertainty, which is also known as the data uncertainty. Okay, so this kind of uncertainty comes from the data generation process and then the natural complexity of the data. So sometimes it is difficult to reduce them. They become irreducible. They come with the data, and that is just the natural complexity of the data. So it's usually difficult to reduce them. Then we have the epistemic uncertainty, also known as the model uncertainty. So it accounts for uncertainty of the model parameters. So this kind of uncertainty can actually be reduced by just like having more data. Maybe your data is not enough for your model to train on. So if you have more data, you could eliminate some of this kind of uncertainty just by training your model well. And then we have the distributional uncertainty. So this is something we call data shift. So it's the situation where you fit a model on a training data that has a distribution that is different from the test data. So it's like you train your model on a certain data and then you introduce the model to some kind of unfamiliar data sets. Okay, so this kind of uncertainties also arise. So this is the whole structure of the deep ensembles. So in deep ensembles, you just basically retrain the same neural network architecture over and over, like several times with different random initializations. And this random initialization helps to make the models like independent as much as possible. And then at the point of prediction, you just use all the models to predict at once, like all of them predict. And then typically most of the time you just use the mean of the predictions as your prediction, and then the variance, the standard deviation, as your measure of uncertainty. And then we have this technique we also call the Monte Carlo dropout. With the Monte Carlo dropout, basically what you do is you train just one model, like one fully connected neural network architecture. And then at the time of prediction, you just randomly switch off some of the nodes. Okay, you switch off a percentage of the nodes. And then this produces different set of models, and then you're able to use all of them to predict. The one feature about this kind of technique is that the models are not completely independent. They share a fraction of their weights. So the models are actually like somehow correlated. Now, okay, so now I'll show you some results. I have a computing artifact that is available on a public GitHub repo. Yeah, so the idea is to get better predictions and also be able to quantify prediction uncertainties. This is just one prediction from prediction of just one data point, one halo from the Monte Carlo dropout technique. And I think I need to emphasize that it's just some kind of coincidence that I got this prediction to look like a normal distribution. Not all the predictions actually look this way. Some of them are skewed and all that, yes. So one thing we did was to compare the mean of the prediction and then the median of the prediction to see which one gives better calibration, because we realize some of the predictions actually have skewed distributions. But I think when we compared, the mean of the prediction is actually a better predictor than the median. So these are just some halos that were random. So this first halo is the first plot I showed you with the analytic density profile. These three halos were randomly selected from the data set, and then we plot the predictions on them alongside with the predictions from our analytic density profiles. Yeah, so I think it's actually sometimes difficult to identify which is doing better than we, because we have several plots, but at least from here, we realize that the prediction from the Monte Carlo dropout looks rather like closer to the actual data, somewhere, I think, in the inner region of the halo, but in the outer region, not so great. I think the deep ensembles is also a bit closer to the actual halo, the actual data set, than the two analytic models. But pretty much, like, I think in this particular region, sometimes it's even difficult to tell because the plots are just overlaying over each other. But the problem is we will not be able to plot all the halos to like visually inspect them. Okay, so this is just another plot I made of the predictions. So I think I actually just thought of something today. Another good measurement will be to check how many of what percentage of our data set actually lie within the calibrated error bars. Yeah, so maybe this is something I'm considering to add to this artifact. Yeah, and then pretty much we see that most of the time we have the predictions, the actual data set lying within the calibrated error bars of our predictions. Yeah, so these are some results. So of course, this is just the various neural network architecture that we considered. And of course, for the analytic density profile, the MSE remains the same no matter what. So, but the problem is we actually have this other measure we call the chi-square measure that we use to determine whether our error bars are realistic, as to whether the error bars are too big or they are too small or they are just okay. So if this figure is closer to 1, then the error bar is realistic. If it is far greater than 1, it means your error bars are too small. And then if it is far less than 1, then it means your error bars are too big. So we realize that sometimes as we achieve a smaller MSE, the chi-square measure rather becomes bigger. And that is a typical example for deep ensembles. The same trend, like the reverse of the trend, seems to be what we are observing in that of Monte Carlo dropout. As we increase the architecture, the MSE becomes bigger, and then the chi-square measure decreases, like it's kind of more of fluctuating. But I think this is a good spot that so the current architecture I'm using and the results I showed you is just basically depending on this simple neural network architecture, and the results is pretty much good. So just a recap, we know that if we understand the dynamics of dark matter halos, it helps us to understand our analytic, our universe in general. And then quantifying, we also notice that the analytic density profiles we have are not able to help us to quantify uncertainties on our predictions, which we think machine learning models can help us to do this. And then we still do not understand the structure, like the mass distribution in the splashback region. And maybe being able to understand this distribution will help us calibrate density profiles more. Yeah, and then we are also yet to discover any significant impact of baryons on high mass halos. So as part of a bigger project, we will consider more data and then like more models. So for instance, as part of a bigger data I'm working on, I'm considering random forest as well, which I actually did not present here. And then I'm also considering the 2D density profile, which is very noisy and difficult to calibrate, which I also did not consider in my computing artifact. But as part of a bigger project, we are considering all this. So I have this computing artifact that is, I think, okay. Yeah, so it's readily available on this GitHub repo. So I don't know, maybe Brian, we can add the link in the YouTube description so that anybody who wants to access this repo can easily access it. Yeah. Okay, so I think that brings me to the end of my presentation. Thank you.
Yeah, thank you, Titus, for this wonderful presentation.
Yeah.
It was really nice to learn new things, actually. Yeah, so at this point in time, we're going to take questions for anybody who has feedback for him, because this is not his final presentation. We'll be presenting on 28th, right?
Yeah, I think 26th of this month.
Yeah, 26th of this month. So if anyone has a feedback of what has presented or any question of him, you can ask now. Yeah, so 10 minutes of questions. Then.
I just have like quick, I don't know if it's a funny question, but it's something that's mentioned in the beginning. Of course, this topic is kind of new to me. I don't know anything. So you're gonna treat me like that something. Why does luminous matter?
Okay, so just think of luminous matter as the matter you can observe by just looking at the galaxy. You know, like when we talk about luminosity, it has something to do with light. So if you look at a galaxy by observation, you could just see the brightest portion of that galaxy. So all the matter contained in that bright portion of the galaxy is what we refer to as the luminous matter. But actually the galaxy region or the halo region go far beyond the visible region of the galaxy. And that is the area dominated by dark matter that we call the dark matter halo. So actually, if you look at the galaxy and you see the brightest portion of the galaxy, the boundary of the halo of that galaxy actually go far beyond that brighter portion. And all this region is dominated by some kind of invisible matter that we don't yet understand. We know they are there, but we don't understand their nature so much well.
How would you know they're there yet they're invisible?
Yeah, so I think I explained earlier on that, okay, maybe, well, since this is on Zoom, I can just basically do this. If I get the image of a spiral galaxy now, okay, spiral galaxy. Okay, so let me just take this first image. Okay, let me just take any image at random. Let's consider this galaxy. So you see, this is the brightest portion, and this galaxy is a spiral galaxy, so that the stars in the galaxy orbit around the galaxy center. So we actually observed that the speed at which these stars move around the orbit center is so much, like it's so high that if the galaxy is made up of only luminous matter, gravity will not be able to hold them bound. They will just move apart, they will split apart. But these stars are still being held bound in their orbits. Okay, so by that, we are able to infer that there is some kind of extra matter in the galaxy that we are not aware of, that is accounting for the extra gravity that is holding these stars in their orbits.
Okay. Does it have anything to do with something you mentioned about like density calibration?
Yeah, so, okay. So the density calibration is actually, okay, so the densities I'm looking at, what I presented in my synthesis is actually not of galaxies, it's of clusters. So like you have a collection of galaxies, a whole lot of them. But at the end of the day, you just have to know that galaxies and galaxy clusters, they live in dark matter halos.
All right, okay. Otherwise, that was a great presentation. Thank you very much.
Yeah, thank you.
Yeah, Titus, I also have a question for you
about
this slide where you presented your network, your neural network.
Okay.
Yeah.
Sorry, just this.
Yeah. About the input space. Yeah, the input space. Are you feeding it to the batch sizes or just the whole data set for each model?
Oh,
because
no,
I can see model 1, model 2, model 3. As in your input space into the machine, to the models. Is it the whole data set or the batch sizes?
No, in batch sizes, not the whole data set.
Okay, so each one have a different distribution or?
Yeah, so what happens is with this particular, the deep ensembles approach, you just randomly initialize the neural networks. And then by randomly initializing them means that each neural network you are fitting will have different weights and biases. So by the different weights and biases, these models become different. Another technique you can use is something we call the bagging technique. Yeah, the bootstrap resampling, which means that you randomly sample from the data and then you fit each model on like a different subset of the data. And then you are able to collect all this. But I think in our case, I tried the bagging technique and it actually severely underestimated the error bars. For some reason, I don't know why. So I'm not using the bagging technique yet, but for the neural network architecture, the data is, I'm using a batch, like the data is fed into the network in batches.
Okay, yeah, thank you. Maybe just another last question. On is it slide 25 on the accuracy?
25. Okay, here.
Yeah, so I can see, is it Einasto?
Okay.
Is the one which is is it more robust to predicting to the quantification?
Okay, so
as
this
in,
is
why is it,
this is actually this is actually the MSE, the mean squared error. So a bigger value means that the prediction is poor. Okay. So the smaller the value means that the predictions are closer to the actual values. So if the value is big, then it means that the predictions are a bit like far from the actual value. So in this situation, I think Einasto is actually not doing good.
More robust to errors. Okay.
Yeah.
Okay. Thank you.
Yeah.
So I have a question about the computing artifact.
Okay.
Yeah. So when you are presenting, you are speaking as if you have big data sets. So how are you putting them here? Like if I want to see how this code works, how will I access this data set?
Okay, so actually the data set, I'm not able to put the data set on GitHub. So I think in the entire data set, I have about 11.2 million data sets. And in my test data alone, I have if I do 80, like 80-20 split, then I'll have like 2.2 million data sets in my test data alone. And this data, the size is huge, so I'm not able to put it on GitHub. But by then, if you want to have access to the data, it's from a simulation and it's readily available. I also kept a documentation here on how to use the code here. But actually, another nice thing I did is to include this folder I call the saved models. Okay, so I just basically saved the models I have fitted, the Keras models. So for instance, if I open this folder for Monte Carlo Dropout, I have this .h5 file that you don't have to necessarily run the whole notebook, the whole algorithm from beginning to end to be able to use the model. Sometimes the training time is like, it takes a long time to train. And I think for the deep ensembles, if I just use it on my like personal laptop, it takes almost 3 hours to train that model. So you can just basically pick this file and then bring it into like your machine or whatsoever, and then you can just use it straight away to do prediction. You don't have to retrain it. Even if you want to, if you have some kind of data sets, I think I would have to add a bit more of the README file to explain some of these things. So if you have a data set that you want to retrain, you just have to make sure that the data set meets the requirement of meet certain requirements, and then you are able to use this model to retrain your data again. So which means that this time your data, your model is not learning from scratch. Your model comes with some kind of pre-trained weights and model architecture. And this situation, the advantage is that it makes the training process faster. And then in some situations, it leads to better accuracy. So it means that you can actually use the models I've built here without necessarily having to. So this is also like, these two are the same. This format is just storing the whole model into one file. This is another format that is also saving the model, but into different files. And yeah, the only difference is that this approach is easier to save, and then it is faster to save, and then if you are loading to, it's faster than this approach. But I think both of them are pretty much doing the same thing. So I have the same format for the deep ensembles as well. The models are saved, so you can just use them.
Thank you.
Yeah, I don't know if that answers your question.
Yeah, it answers it.
Okay.
Thank you.
Any other question? Yeah, so I think we've come to an end of this presentation. Titus, thank you so much, and we wish you all the best in your presentation on 26th October. And we are hoping to attend again. Just make sure that you share the link with us.
Okay, sure.
Yeah.
I think it's going to be in person.
Oh, it's going to be in person?
Yeah, but
Yeah, just share the
I'll
venue.
give you the details. Yeah, sure.
Yeah.
Okay.
Thank you so much. It was really wonderful to hear from you. Yeah. So next week, this is a SIAM presentation. We'll still be having a series of presentations. So next week we'll be having Damien. I'm sure we've communicated with you via email. Brand sent an email out, yeah, to everyone. So we're hoping to meet you again, same time. Yeah. Damien will give us a talk, same as Titus, but we'll be talking about what he did during his internship. Yeah, I think that's for now. I don't know, maybe closing remarks from Brand. Anything, announcements or?
Yeah, thanks everyone for coming, and we are always happy for you guys coming out here and yeah, engage in our events. Thank you very much.
Okay. Okay. Have a wonderful evening. Thank you. See you next week.
Okay, thank you. Thank you,
Okay.
guys.
Thank you.